So, welcome back students. We are basically discussing functional group based strategies, and last class or last week lecture we have talked about how different skeletons can be disconnected through a functional group based approach, and I said that a key transformation is always essential to find it out. You need to find it out the key transformation, which is basically very essential. Now, today we will be talking about the second point, which is how you can use multiple key transformation based approach for a given functional group based retro. Now, initially when you basically discussing the functional group based strategy, you said there are 6 guidelines which will follow. The first one basically functional group based skeletal disconnection, where we said that you have a skeleton given to you in a target molecule and you just try to disconnect the skeleton through a single and uniform key transformation. Here we are trying to follow the similar pathway, but here we will try to explore if there is a multiple key transformation is available. So, means that the target molecule essentially will be little bit complex here, where you need to find it out more than one key transformation will be needed, but definitely we will trying to do a skeletal disconnection. The initial problem which I was given to you for this set, it is a basically a complex carbocycle skeleton, and there are having 4 different ring. Let me first complete the structure, and now you will find that this compound here is having another bridge structure. This is a bridge structure. So, 5 member ring 1, 2, this is 6 member ring, and in between the 6 member ring you have a bridge unit, Now, essentially once the target structure was revealing to you or target structure is known to you, and I have not given the starting material. Definitely, as I said, this is a complex phenomena, complex scenario, where you can definitely think about that where from to start. And now, I will first try to do the retro based on simple functional group addition elimination, then you try to correlate or try to connect how these things can be created. Initially, I said that we will do some hydrogenation here. Now, eventually you may ask that sir, why this hydrogenation was the first step you have chosen. Now, as I said, definitely the logic must be there, but that visualization probably experienced people can think about, and this experienced people when they are doing this retro, they found that probably hydrogenation will give you some interesting skeletal disconnection. Now, next skeletal disconnection what I am trying to figure it out is the most crucial part in the entire pathway. We said if you have a structure like this, okay, and then this structure has been envisioned that you basically do a the structure was little bit wrong. So, we will try to do the right structure again. As I said, the target is pretty complex, sometimes small mistakes do happen, and I am sorry for that, but eventually the entire structure was a bit complicated. So, now is correct. Now, what is said? I say if you having a tertiary alcohol of this structure and now you try to figure it out, this structure is basically nothing but it is a 1 2 3 3, I mean this is a pi network on the left hand side, there is another pi 1 2 3. Now, this 2 pi network basically is trying to have a, so 1 2 3, I write 1 2 3, this is a right 1 2 3. Now, this basically fits into the perfectly a sigmatropic rearrangement based transformation. Now, once this in the real sense, once the transformation was done, basically what we do, you come here, okay, and then this comes here, and then particularly this things comes there on this back of this bond. So, this particular visualization is little bit difficult until and unless you are quite know or quite sure. As I am taking, you please try to do this practice in your home for this particular transformation. As you are dealing with little bit complex system, you please try to figure it out that. Now, I said it is a 1 2 3 1 2 3 and then is a 1 2 3. So, what I am basically this comes, this is a direct connection for this with this with this pi bond comes here and this comes here. Okay. Now, you are basically getting a pi bond here which is now a enol. Now, this enol basically tautomerizes to give you this ketone, and this particular pi bond is basically which is the pi bond which is now generated here. So, is a clear case of 3 sigmatropic rearrangement reaction, and that is in real practice that how this structure can be correlated this target molecule. Now, I said this is very difficult, definitely it is difficult, you need to practice a couple of times in your home to coming from this structure to this structure. So, fine, now once we have this particular structure, your next thing will be how you can make this molecule. This probably you can think of making this molecule by a simple carbonyl addition reaction. If you are having this carbonyl and you are having this bridged bicyclic vinylic bromo compound as your electrophilic or sorry is a nucleophilic, you can just exchange this bromine with a magnesium or lithium, you create the corresponding vinylic Grignard species, react it here. But nevertheless, how you can get that target molecule or how you can access this intermediate also. So, the intermediate now is basically this intermediate as well as this intermediate, fine. This intermediate will be saying that now a Diels-Alder transformation is very useful. So, we say you do a Diels-Alder with this dimethoxycyclopentadiene with a standard dienophile something like this or a nitromethane. This is already discussed in earlier slides, fine. Now, this compound you can again think about doing a Diels-Alder reaction definitely. Let us say if you having a compound like this, this compound is basically nothing, this compound is this compound, is not it. So, means that now how you can prepare this compound is absolutely fine. You take cyclopentadiene with similar kind of lead cellular reaction and do hydrogenation, that will basically give you. Now, from this to this, basically you need to convert this compound with a vinylic species something like this, which you can basically easily react with a bromonium ion to get a vinylic bromide. Now, actually this reaction in principle can be done by a reaction named as Shapiro reaction. Shapiro reaction. We have not discussed it, the Shapiro reaction, but probably Shapiro reaction is a very useful reaction. Again, if you are looking for the mechanism, go to scenearchive.com. Naturally, remember in the latter part of our discussion, we will talk about some of the specific reactions. Now, Shapiro reaction is very useful. Shapiro reaction, I will just now give you the disconnection. Shapiro reaction is a very useful reaction and the particular in terms of if you having some compound like this, you can easily convert this compound to this minus. Now, this minus basically can be quenched by varieties way with several electrophile. The electrophile could be anything, it could react with simple bromonium ion, it could be CHO plus, could be other electrophile like carbon dioxide. So, basically if you react with bromine, it will give you a vinylic bromo species, it will react with a dimethyl formamide to give you a corresponding aldehyde, it will react with carbon dioxide to give you corresponding carboxylic acid. Shapiro reaction, what exactly was used? We used a tosyl hydrazine and then treat with a excess base butyl lithium, that basically gives you a vinylic anion. The mechanism, as I said, we probably might have discussed it, I do not remember exactly, but please go to the earlier slides. If it is not discussed, you can just go to the scenearchive.com to find the mechanism in detail, and remember probably in the couple of next lecture we will be talking about some specific transformation based synthetic approaches where you can find. So, if you now come back to the original problem where you have started, you will find that this particular retro, we started with a very complex molecule, we said this very complex molecule we started, and the only thing is no starting material, nothing was available. So, that is really tough. We said that a 3,3 sigmatopic reaction was the key reaction which was performed to this intermediate. Now, I said that please make a practice in your home that how this intermediate or this structure is undergoing 3,3 sigmatopic rearrangement to give you this one. It is basically a simple bond breaking and bond making. The arrow shifting I have shown you, this things is connected to this and this bond is going to be chopped down, you make a new double bond here. So, it is not easy, but it is not difficult also. So, you have to do it, and once you can you have done it, then you can find that there are two intermediates we are talking about, and particularly the transformation which we are basically looking is a combination of several multiple transformation. So, now if you see the transformation which we use is based on multiple transformation, multiple key transformations for a skeletal disconnection, multiple key transformation for skeletal disconnection. Transformation what we basically used a 3,3 sigmatropic reaction, Then we used couple of lead cellular reaction to access both the intermediates. Okay. Then also we said a Shapiro reaction was used, very useful reaction. So, in this way several different kind of multiple transformation based approach can be used to construct a core structure of the given molecule. Now, remember this kind of multiple transformation based strategies also we have discussed it when we talked about transformation based strategies. So, in principle this multiple transformation based functional group based KIT skeletal disconnection, it is similar. You can just think about combination of using a multiple transformations and how the target molecule was assembled in a efficient way. The point 3 in the functional group based strategies, now we will try to explore something different. We will be calling it strategic use of functional group equivalent or synthetic equivalents, functional group equivalents, and now we termed this group as synthetic equivalents. We will explain what are these synthetic equivalents. We will try to give you a simple target, and actually if you recollect the earlier lectures we have already discussed this strategy by several reactions. We said the target molecule is this compound, starting material was this. Now, basically the retro which we are talking about is if you having a CHO minus species or this functional group species, which is nothing, in reality it is Ampolong species, can be constructed through a different way, because this is not a commercial available, this is not commercial available. Commercially available. Now, this particular species we call is a synthetic equivalents or functional group equivalents of a formyl anion. This is nothing a formyl anion. So, if somehow you are having a formyl anion in your disposal, you can basically do this carbon carbon bond formation. And actually probably all you know that where from this formyl anion can be generated, but this is basically we talked about strategic use of functional group equivalents or synthetic equivalents. Now, what is this? It basically says that this formyl anion is a synthetic equivalents and it can be generated from a 1,3-dithione species of a formaldehyde, or this anion also can be generated from a nitromethane. Now, come to the real system what we initially proposed, which is cyclohexenone. First take a base sodium hydroxide and react with nitromethane. Nitromethane will basically generate the anion and it will undergo Michael addition. Now, Nafe reaction we have already talked about, Nafe reaction. So, this reaction will now give you CHO. So, what is this? So, nitromethane can be a potentially considered as a synthetic equivalent of a formyl anion. Same way you can basically pick up both these acidic hydrogens or one of the acidic hydrogen to replace with a lithium species. Lithium. Now, this lithium can undergo a 1,4 attack here. So, this will attack in the 1,4 fashion to basically give you right, and then you basically just clip this with a mercury and you get a CHO. So, this also this formaldehyde dithione is also a synthetic equivalent of a formyl anion. So, our next couple of problems which will basically based on this kind of concept, where you can strategically choose a functional group which is reality can be envisioned or can be constructed through some potentially synthetic equivalents which are in principle is commercially not available, but are very valuable synthetic intermediates. Now, before we talk about these things, we will try to give you examples of or explanation about two terms D and A. We might have explained it couple of times earlier. D stands for donor and A stands for acceptor. Actually, we are planning to give you a in depth analysis of synthetic equivalents little bit later on at the end of our main lecture. Then you can try to talk those things in detail. Donor means that whenever you have a negative charge in the synthetic equivalents, it can donate its electron to a electrophile. An acceptor which can accept the electron. Now, in that category, your formyl anion 1,3-formyl dithione, when you react with base, it basically gives you a carbanion, this minus. Now, this minus is basically nothing, is a D1 species. D means stands for donor and 1 stands for 1 carbon, this basically gives you 1 carbon, right. An acceptor are similar, very well known acceptor is something like if you having a compound like this. So, this is a acceptor which can accept a donor, this is basically a Michael acceptor. So, this is acceptor and this is a donor which can react. So, one of this next problem which basically deals with a compound whose structure is something like this. We said a target molecule which was given to you having structure like this. Okay. Now, the target was given to you, the starting material was also given to you. The starting material I say is having this structure. So, now if you closely analyze the functional group content, only functional group which was added here, it is a this CHO. So, this is basically a double bond, you adding a CHO and a OH. So, is a two functional group which was added in the starting material to give you the target molecule. Now, do the retro in a very classical way. I say if you having this epoxide and you are having a this formyl anion as a source of nucleophile or a D1 species. Now, I say this epoxide can attack either this way as well as this way. Now, definitely the red path which is sterically less favored or sterically disfavored, because it is having a bulky benzyl group in this carbon, but this carbon does not have any such steric crowding. So, epoxide opening is always preferred from the less inner site. So, now you can correlate that if you have this starting material, you just make this corresponding epoxide through a MCPBA mediated epoxidation, your job is done. So, for the forward pathway it is as simple as that. You start with the corresponding olefin, react with MCPBA, you get the corresponding epoxide, then CHO minus. Now, as I said, CHO minus is not commercially available, it is not in the bench or the rack, you can get it. So, basically you react with either nitromethane plus sodium hydroxide, which basically give you a CH2 minus NO2, or take a this formaldehyde ampolone 1 equivalent with lithium. So, any of these either synthetic equivalents S1 or S2 can be basically reacted either this mainly this carbon as well as this carbon. So, what basically you will get in this case, you will get OH CH2NO2, and this case you will basically get your entire diethane part. Next is you do a Nafe reaction here to complete the synthesis. Here you do the same thing by mercury mediated cleavage. So, basically what you expect that you can use strategically two reagents at parallel step. Both the reagents can serve as a formyl anion precursor. Both the reagents like nitromethane and anion generated here and this 1,3-diethane formaldehyde lithiated species can also serve as a formyl anion equivalent. And the initial retro which was purely based on a functional group based approaches, and the key reaction which I said is a ampolone addition on a electrophilic epoxide, and obviously the stereochemistry of the epoxide has a clear cut role in the entire pathway. Next 2-3 minutes I will just trying to explain I say a target molecule was given to you a cyclohexanone, fine, and then you now starting material was also given to you 1, 2, 3, 4, 5 Br. I said this C5 dihalogenated species was given a starting material. Now, we are basically discussing the concept of synthetic equivalence, concept of synthetic equivalence. Now, this compound is a starting material is having a only carbonyl functionality, and based on these things if you try to disconnect here and here, what basically you will get? You basically get a doubly charged species and this double electrophile. So, means that if you now disconnect this way, that this minus react here, this minus react here. Now, this particular species which I have now drawn here is named as a 2D1 species. Now, D stands for donor, 1 for 1 carbon and 2 for doubly negative, that there is 2 negative charge. Now, if you try to correlate with this C5 synthon which is having double positive charge, this is the starting material. The starting material one end having iodo, one end having bromo. So, now what exactly you basically will be doing this synthesis? You first take the formaldehyde 1,3-diethiene, react with 1 equivalent of base and react with this iodo or bromo, any of this iodo is supposed to be more reactive. So, first you react with this entire thing and you get this compound, this bromo. This hydrogen remains here, you react with 1 equivalent of base further, that will generate the anion and you then make the carbon carbon bond and you cleave with Hg2 plus, that will basically give you your or complete the synthesis. So, in principle synthesis by using this synthetic equivalents are very fantastic. The only point is you have to be quite sure that which bond you are going to be disconnected and what are the synthetic equivalents we are mainly focused on. Now, mainly the synthetic equivalents which are very popular we will try to disclose in this particular lecture, and in the final part we may discuss some of the very unpopular synthetic equivalents, but synthetic equivalents like this formyl anion, which is can serve as a D1 species as well as 2D1 species. It is very useful, very popular, and mainly we will try to focus on this kind of for Ampolong synthetic equivalents in our next couple of lectures, where we talk about the functional group based strategies. So, till then, goodbye, have a good time.